Now let's take integration and develop what we call Riemann sums to define the definite integral and be able to put some precision into what integration really is by defining it numerically. So the Riemann sum is what we've been doing. If you looked at the previous screencast, when we took an interval of a region under a curve between endpoints A and B and divided it up into intervals, partitioned it into intervals, what we have when we find the areas of those individual rectangles and sum them together is called a Riemann sum. A Riemann sum goes from a point A to a point B along a curve, partitions it into rectangles of width delta x. And oh, by the way, we've had constant widths of delta x, but it need not be constant. So delta x is the width, and f of x sub I, the individual height of the rectangle. So let's link that to the definite integral. The definite integral of a function is the Riemann sum of the region when we go from A to B, and we partition it into not just a finite number of rectangles, but an infinite number of rectangles as the width begins to approach zero. As that delta x goes towards, but never quite gets to zero, we wind up with an infinite number of rectangles that we're summing. So once we've done that, we actually find the exact area under a curve. This is an incredibly powerful part of calculus. So let's talk about some terminology, because this is the Riemann sum definition of the definite integral, but this left-hand part is what you're going to be focused on a lot, and that is finding what are called definite integrals. Now you already know this stretched out S is the symbol for integration. It's much related to the Greek sigma. It is the summation. So we're summing things up from a lower limit, A, to the upper limit. So the number on the bottom is going to be the lower limit of integration. The number on top is the upper limit of integration when we have a definite integral. Now, indefinite integrals, which we've covered already to a certain extent, don't have these numbers. So they produce an infinite number of solutions. These definite integrals are going to give us one solution. F of x dx is what we're integrating. The f of x is the function, which represents the height of each of those rectangles in the Riemann sum, and the dx represents the delta x, the width of the rectangles, which gets infinitely close to zero. So let's look at the area of or under a function and define it as the definite integral. So as long as the function is continuous and non-negative on an interval, a to b, then the area bounded by the function, the x-axis and the lines x equals a and x equals b, is defined as the definite integral, where a and b are the lower and upper limits of integration, and f of x dx is the Riemann sum of those rectangles. Now this definition says non-negative, but we are going to look at examples where f of x is negative, and we can deal with that as well. And it all depends on the application. We'll get to that. So let's look at some properties of definite integration. First of all, the zero integral. If our starting and ending points are the same, then the area is zero. We started and ended at the same point, we really have no area at all. So the integral from a to a of f of x dx is zero. Let's look at a negative integral. If we go from a lower limit of b to an upper limit of a of f of x dx, that's equal to the negative of the reversing the endpoints from a to b of f of x dx. So if we interchange the endpoints, we wind up with a negative of the original value. If we have a function that is broken up into parts, in other words, we have an interval from a to b, where a and b are the lower and upper limits of integration, and we're finding the area of this function, then the integral from a to b over the entire interval is equal to all the subintervals added together. For example, if we broke up this interval ab at a point x equals c, somewhere along the interval, the integral of the whole thing would be equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. We have a continuous function. We can break it up, decompose it into parts, and the area of those parts should add up to the area of the whole thing. There is also a constant multiple rule for definite integration. The integral from a to b of a constant times f of x dx is equal to the constant times the definite integral of f of x dx from a to b. So we can, just like an indefinite integration, pull the constant out. There is also a sum and difference rule for definite integration as well. The combined function of f of x plus g of x, their areas are equal to the areas of f of x plus or minus the area of g of x. So we can break up those functions into parts, which makes sense because we're dealing with areas here, and areas are additive. So here's your math joke of the screencast. Volume of disk with radius z and depth equals a. So let's look at the example that we were dealing with earlier, which is f of x equals the square root of x plus 2 from x equals 1 to x equals 5. And we wanted to find the area underneath that. Now, we used a Riemann sum with 4 rectangles before and found a reasonably close approximation. We can find the exact area under this curve, between this curve and the x-axis and these two x values, by using definite integration and a Riemann sum using an infinite number of rectangles where the width approaches 0. And we would write that like this. The area is equal to the definite integral from 1 to 5 of the square root of x plus 2 dx, which breaks that interval from 1 to 5 into an infinite number of infinitely small in width rectangles. And when you learn how to evaluate definite integrals, which we're going to do in the next screencast, you'll be able to find that exact value. But for now, knowing how to set it up is the important thing. Oh, by the way, let's talk about some properties of definite integrals using this tangible example of this function, the square root of x plus 2. If we were to integrate this function from 1 to 1, starting at 1 and ending at 1, the integral from 1 to 1 of the square root of x plus 2 dx is equal to 0. If we were to integrate it backwards, instead of going from 1 to 5, we went from 5 to 1, the integral from 1 to 5 of the square root of x plus 2 dx is equal to the negative of the integral from 5 to 1 of the square root of x plus 2 dx. Also, we can break this up into subintervals. The integral from 1 to 5 of the square root of x plus 2 dx is equal to the integral from 1 to 2 plus the integral from 2 to 5 of the same function. So in other words, if we were to break this whole region into two smaller areas, one which went from 1 to 2 and another one went from 2 to 5, the combined area would still be the area combination of the two. And finally, the integral from 1 to 5 of the square root of x plus 2 dx is also separable. We can break this into two separate integrals where we have the integral from 1 to 5 of the square root of x dx plus the integral from 1 to 5 of 2 dx. And in fact, you can kind of see this graphically. If I just take the square root of x function right here and found that area, and then just found the area of the function y equals f of x equals 2, the rectangle there, and added those two areas together, combined they would be the same area. We took the area of the rectangle, 1 to 5 of 2 dx, and the area of the square root function, combined they equal the same area. So lots of different ways to break these things up, lots of different properties of definite. Next screencast, we're going to discover the fundamental theorem of calculus and use it to find definite integrals. So in this screencast, we looked at how a Riemann sum, where we let the number of rectangles be infinite, gives us a thing called the definite integral, which allows us to find areas under functions and leads to some powerful things.